Hi, you might notice that I'm not here today. So I'm at a meeting at district office. I will be back to Chaska Middle School East today in the middle of fifth hour, so I'll be around at lunchtime if you need to talk to me. I also will be available after school today for kids who need to work on some learning targets. Also on Thursday, I'll be available after school, and for Friday, I'll be available till about 3:30. I can't meet with people on Wednesday because I have a meeting after school. And then we will have 3 flex times, but if you're someone who has more than one learning target to take care of, you need to come in after school, or make a plan with me to figure out what you can do to make up those learning targets. So you want to be sure you're talking to me one-on-one. You should already have your textbooks when you came in. This was up on the screen. So you open up to page 156, and I'll be talking about that in a minute. Also, the substitute teacher will be passing out the assignment that you're working on for notes for absolute dating. And that's something you're going to want to hold on to because you will turn it in with your decay graph after block. So the first thing that I wanted to talk about is what I mentioned on Friday. We're finishing up our learning targets, so you can see kind of how they're laid out. This decay graph, which is on 2.3, will be turned in after block. We'll do the graph right in class. There's some questions you could turn in Friday too if you need to follow up on that. Friday we did this uniformitarianism catastrophism, learning target 3.3. And don't forget about the water cycle. Some of you just need to answer question number 4 on the notes, and then you'd be at a MEETS level most likely. So that's for the water cycle. The geologic timeline is the yellow sheet, and on Earth and Minnesota timeline where you did a comparison. This relative dating puzzle is 6.2, and then climate change was due last Friday. So those are the learning targets that I want to make sure you're aware of. Also, we have the relative dating puzzle. So you have this picture that you drew, something like this, maybe not quite as complicated. That's on one side, and then on the other side are the directions, and then you needed to explain what each layer is. So layer 1, step 1 is layer E deposited. Step 2, K, is erosion. And so on this one, they don't show erosion with a letter, but that would be this right here. Layer G deposited, layer I deposited, B layers tilt. So I just made that up, and you would have like the letter B on the side someplace. And then this actually says H is the fault line, but you just have to write the word fault next to the letter that's showing the fault. So this steps through 12, or if you did extra, that's fine, but that's all you have to do is explain each step like this. On Friday, we did the Earth History Uniformitarianism Catastrophism assignment. You look for the Trilobite Earth History and Empower. You're clicking on Uniformitarianism Catastrophism. You're going to drop this document into your locker. And some kids have already turned this in, and I've already graded it. So take a look and see how you did. But this is where you're creating a product, doesn't matter, whatever you want to do, to demonstrate your understanding of those two terms, catastrophism and uniformitarianism. And the scoring guide down here is to help you know what I'm looking for. But I did put these questions, so if you give a definition in your own words, or maybe have a definition and then underneath it say in your own words what it means for catastrophism and uniformitarianism, and then give examples. There's an S there, so I'm expecting 2. And explain how that's catastrophism and examples for uniformitarianism and why it fits that. And then this is for extending. So why is the Earth's surface the way it is today? Is it because of catastrophism or uniformitarianism? And you kind of argue your point. I do have some definitions underneath. These are examples of products. So I already have a student who turned in an infographic. You might do a Google Slides. You might do a mind map, however you want to show what you know. And you can take a look at these 2 definitions I provided. Also on the Week at a Glance, I have the book pages that you use to help you with this. So this is what we're working on today. I'm going to go back to the Week at a Glance so you can see that. So for this week, we have a picture of radioactive decay at the top. Uranium has a neutron turn into a proton, it becomes neptunium. And then another particle is excited, turns into plutonium. So that's showing this chain of radioactive decay. This is the t-shirt I'm wearing today for T-Shirt Tuesday, carbon dating. And you can see here the book reading is linked here. The notes is linked in this presentation. Here's what's due. And we're going to be doing this Penny Lab tomorrow, so I stuck that. And your radioactive decay graph. And then last Friday, there it is. I put the textbook pages in, so you can click on that if you need to look at what we read in the textbook. It's there, or you can look in the textbook that you have right now. So page 152 and 153. That's just to help you out if you were absent. So let's go back to what we're doing today. So in your textbook, there's page 156 that you're on. You can see it has some definitions, and the key thing that I want you to be looking at is this paragraph with relative dating highlighted and then a definition off to the side. I think that'll be helpful for you to look at for the notes that you're working on today. And then you'll skip on to the next chapter, section 3 for chapter 6, but there's some things in here that'll help you if you're not done with your relative dating puzzle. You can see how it explains how the fault would look, how an intrusion looks, folding, tilting. So take a look at that if you're kind of stuck. They even have like a little mini puzzle here you can take a look at. All right, so now we're heading to page 162, 163. And if you look at the assignment that we're going to be working on, you can see this first part, you're just writing the definition for relative dating and then showing a picture to demonstrate that. And we've talked about this where things that are on the bottom are older, things that are on the top are younger. So it's just that relationship of where they're located. And then we have absolute dating, so definition, and then comparing the difference between relative and absolute. All right, so let's go back to in the textbook. So here it talks about radioactive decay, and an isotope, remember, is a special kind of atom that has more or less neutrons than an element on the periodic table. And the isotopes that we're looking at for when we're dating something, absolute dating something, is that it's radioactive, and so it has this decay cycle. And you can see down here there's this unstable isotope of an element, and it has 6 protons and 8 neutrons. So you should know which element that is, and if you don't, you might want to sing the song. There's hydrogen and helium, lithium, beryllium. You guys know the rest, so figure out which element this is, and then it gets excited, a neutron turns into a proton, and now it has 7 protons and 7 neutrons. So what element did it become? So this is the parent and this is the daughter. And you can read about that right here where it talks about the parent isotope and the daughter isotope. So when you're comparing, when you have a specimen or some kind of like a rock or something, you can look and see how much of the parent and then this daughter isotope are in that sample. And if it's half and half or equal amounts of each, then you know it went through one half-life and you can figure out how old it is. Now this may sound really kind of complicated, but it's not. It's sort of like when you have popcorn that you're going to pop in the microwave. If you just do it for half the amount of time, only half of the kernels are going to pop and the other half will be popped. So you know that you didn't do it quite long enough. When it pops through everything, then you know you've reached that limit. So it's sort of, think of it that way. But radiometric dating is looking at the comparison of the parent isotope compared to the daughter most of the time. All right, these pages are different types of radiometric dating. So if you look here, we have potassium and argon. So potassium is the parent isotope, argon is the daughter isotope, and a half-life for the this isotope is 1.3 billion years. And it does produce calcium too, but scientists only look at the amount of argon that's left or produced. So it's used for rocks that are older than 100,000 years old. So you'll fill this in on a chart, but that's the part that kids kind of get stuck on. So the parent is potassium, the daughter is argon. And this one's unique because it also produces calcium. So then this one says uranium lead method, and here it says rubidium strontium. I want to point out that on here it says 49 billion years is the half-life. But if you look in some textbooks, some of you out there might have a textbook where it says 49 million, which is incorrect. So when you get your sheet, cross out million, it should be billion, and then you can figure out these two. The number here is how many neutrons it has, so try and include that number too. The last part are these challenge questions. So carbon dating is a little different than using radiometric half-life. Explain how the age of an object is found using carbon-14 method. How is this different than radiometric dating? It's kind of an interesting relationship, and you can read about that right here. Then the other challenge question is you have this African tribal artifact that's buried in sand. What isotope would scientists look for to determine the age of the object, and why did you choose that isotope? So you're going to need to look at this reading here and here too to help you figure out what you might use. And then question 3 says, when a meteor is found, scientists look for a particular isotope to determine the age of the object. Which isotope would be used to determine the age of a meteor, and why? And meteors are similar in age to the Earth, so that can give you an idea of how old it could possibly be and what would make sense to use. So be careful, because it needs to have a pretty long half-life to be able to tell the age of it. And then going further, I would really like you to try this. It says scientists use radioactive isotopes for medicine. Research this topic on the internet and find at least one isotope. You'll be looking for an element name used in medicine. Include the parent and daughter isotope and the half-life. Why and how are the isotopes used in medicine? Sometimes it's hard to find the daughter isotope. If you can't, don't worry about it. I put a link on my right here on my Week at a Glance Google presentation. So if you click on that, this could be what you use, but it doesn't tell you the daughter isotope, so you'll have to do a little more research. And then make sure it makes sense to you, or that you can tell what it is actually used for. Like the first one, reactor radioisotopes, half-life indicated. That's just telling you what this is, so you need to make sure it makes sense. And the next one, molybdenum 99, has 66-hour half-life, but that's the parent that's used to make technetium, which is the element that's used for all these body parts. So try and do something different that somebody doesn't have. This is how long the list is. So there's a bunch of them, but it's kind of interesting, especially if you're somebody who's really interested in biology. This would be a good place to start. You certainly can look up your own information, but I thought I'd help you out. And for the challenge questions, I would like you to try and have 1 or 2 done. It would be great if you had 3, but that's fine if you just have 1 or 2, and then move on to the going further. And that's what you're working on today. When you're finished, you have plenty of stuff to get done. So check on your global work, maybe grab a laptop and look in Empower to see what was graded, or if you're missing anything. And let me know if you have any questions. I'll be around at lunchtime. Like I said, I'll probably be up in my room, not downstairs, but check in with me if you need anything. Have a good day. Thanks.